Hi all, welcome to our conversation on bacteria, archaea, and protists. Today we're going to cover a really broad diversity of organisms. Some of those organisms are very similar to those that were the first organisms on Earth. In this visualization, this tree of life, you can see that from the first organism, which is a common ancestor of all life on Earth, that direct lineage results in bacteria. So those first organisms likely were bacteria or extremely similar to bacteria. An offshoot of bacteria are archaea, and it's only later in the history of Earth's evolution that you get the development of eukaryotes and this really broad radiation of life that includes us way over here somewhere. In order to talk about the ancestry of bacteria and archaea, you have to actually go back to the origins of life on Earth. So here's an illustration showing the evolutionary history of life on Earth and the diversity as it arose on this timeline. So what's important here to note is that the sun ignited, or the solar system kind of began functioning about 5 billion years ago. The Earth finished its coalescence and finished developing about 4.6 billion years ago. And so life couldn't have started until that point. But somewhere between 4 and 5 billion years ago, we had this massive celestial body hit the Earth, and that was the moon. That was a pretty significant event, and it's unlikely that anything could have survived that event. So life really couldn't have started until after the moon hit the Earth, bounced off, and then began orbiting. And if you didn't know, that's likely why the Earth's rotation is off tilted to one side and why the Earth spins at the rate it does from that massive impact. Between 4 and 5 billion years ago, life would have had a pretty tough time starting. But let's say that sometime after the moon hit, that's when kind of the race towards life beginning on Earth started. Well, it didn't take very long for those first organisms to evolve. You can see here that the first organisms have been detected somewhere around 3.9 billion years ago. So it took less than a billion years from the beginning of Earth, the formation of Earth, to the first living organisms. That's pretty incredible, especially when you consider that the overall age of the Earth is somewhere around 4.6 billion years. So if that's the case, then life started almost immediately. Life has been around on Earth much longer than it has not been. And it seems like as soon as conditions stabilized after that impact with the moon, life began. But how did that happen? To understand how life could have begun on Earth, we kind of have to pull from a lot of different concepts that we've learned throughout the semester. Some of that's a little bit of light chemistry. We're going to have to talk about macromolecules. We'll have to talk about energy and how energy affects systems. And when we put all those things together, we can start to build a picture of how these kind of first proto-organisms, these first living systems began. What did the Earth look like just before life began? And those are the conditions that we want to look at when we try to understand how life could have started on Earth. It's kind of like Earth before living things. Early Earth probably looked something like this. There was a few different gases present. Remember, there was no oxygen yet because that's a byproduct of respiration and living things. But there was probably methane, ammonia, water, and a lot of different geological factors like volcanic activity, deep sea vents. There was also lightning. Taking all of these kind of ingredients into account, Stanley Miller in 1953 developed this classic experiment that really illustrates how we can go from a bunch of inorganic material and inorganic compounds to the basic building blocks that life needs in order to structure itself. The basic outline of the Miller experiment was that he replicated the atmosphere. This whole system here is sealed off, and it's filled with water, ammonia, nitrogen, and with hydrogen in gas form. Within this system, he has cold water to condense the gas. Down here, there's a place where that can coalesce, it can collect, so that would be like an ocean. And then there's a heat source, which would be something like either solar radiation or maybe volcanic activity or geothermal sources of heat, that then evaporates that water and also other material back into the atmosphere. So in that sense, this is kind of like a model for Earth's early system. The important factor and feature in this experiment that really replicates conditions in early Earth is this electrode here, and that's simulating lightning. So the idea is that lightning introduces a very high amount of energy, and that energy allows these basic molecules to reform. It's kind of like a catalyst and catalyzes the reformation of these molecules into different compounds and different kind of building blocks. What he did was he let this run, and by run we mean he heated that water on one side, that evaporated, and that moved through the system where it condensed and created a cycle, which is kind of like our hydrological cycle of rainwater and ocean water. And then while it was running, he introduced sparks which simulated lightning in the atmosphere. And after he ran that for a while, he noticed that the water in that coalition chamber, in that simulated ocean, had actually turned pink. It had turned color. And when he analyzed that, he found that there was amino acids that are used in biological organisms in their basic functions. This experiment resulted in 11 different amino acids, and those compounds were not present in the early Earth's atmosphere. That was a result of lightning, high energy input reorganizing the available material into these more complicated compounds. This experiment helped illustrate how we can go from some basic common ingredients that are found in celestial systems that are newly formed to organic molecules and compounds necessary for the beginning of life. Now, what it doesn't explain is how those molecules structured themselves and became living systems that could reproduce and fulfill our definition of life on Earth. That requires a little more in-depth explanation, and I'll leave that to some other videos to explain just how that organizational process occurred. But the end result of these organizations of molecules on different surfaces was eventually an ancestor to all living things on Earth, our last universal common ancestor. You can think of the last universal common ancestor as your great-great-great-great-great-grandparent. This individual organism stemmed all life on Earth, including bacteria, archaea, all eukaryotes, plants, fungi. And so the story really starts there. And that's where we can start to explore the diversity of life on Earth.